Welcome to section 6.3. So we've talked about multiplying and dividing radical expressions, and now we're going to talk about adding and subtracting them. Now once again, this is an idea. You got the basics of this back in exponential algebra, all right? Now we're going to develop those skills further to talk about higher order radicals, okay? Higher indices. So steps to adding and subtracting radicals. First, if you can simplify the radical, you need to do so, okay? So simplify first, then check to see if the terms make them like radicals, okay? Now, one little rule, add or subtract the coefficient that's outside the radical, but do not change inside the radical. So if you look at the examples in this chart here, for example, you have 1 plus 3 gives you the 4, but notice that the square root of 2 doesn't change, all right? Here you have a 1 minus 5 gives you a negative 4, but note that the square root of 7, again, doesn't change. You're adding and subtracting the outsides, not adding and subtracting the insides. However, this only works with like radicals though, okay? So what I mean by that is I have two examples here that don't work, okay? And let's identify why they wouldn't work, why we can't combine them. Well, here, if you notice, those are not like radicals because you have a different radicand. Okay? If you have different values inside the square root, it's not going to work. For this one, I notice the radical itself is different, okay? If you have a different index or different indices, they're not going to work either, okay? You're not going to be able to put them together. So just keep that in mind, the rules of when can I combine them together, okay? Because those are two instances where it would not work. However, of course, for the most part, we want to talk about things that do work because that's the kind of the focus of math. Why would I give you a ton of problems you couldn't actually do? So let's focus on what it looks like when they can actually simplify together. So here, I have 3 square roots of 14 plus 7 square roots of 14. So the radicals are in fact the same. They're both a square root and they both have a 14 inside. So if I have 3 of them and I'm adding 7 more, I just get 10 square roots of 14, right? As simple as that. All right, for this next one, I have 2 square roots of 7 minus 8 square roots of 7. So that's going to give me a negative 6 square root of 7. And what you notice is then I have a square root of 10. So now the square root of 10 piece isn't going to be able to combine. So I combine those square roots of 7s together, but then the square root of 10 is going to remain on its own, okay? It's going to remain as a separate radical. And same rules apply even if you have a variable there, right? So 5 cube roots of 3x plus 4 cube roots of 3x minus 1 cube root of 3x. So 5 plus 4 gives me 9, minus 1 gives me 8 of those cube root of 3x's. So the same thing applies even if I have a variable there as well. All right, so there's some basics. Now let's work on getting a little bit harder. So remember when I started the notes, I talked about that you should simplify first if you can. All right, so what that means is here right now, all of those look different, correct? Square root of 12x squared, square root of 75x squared, square root of 3x squared. So right now they all look different, but if you simplify them, you're going to notice something really cool that happens. So here, that square root of 12. Square root of 12 can break up into 4 and 3, right? And again, using the 4 because it is a square root, okay? It's on, let's see if I still have it up, it's on my powers chart right here. under the second power, okay? So remember, you're still using that power chart when you need to. So the square root of 4 is going to be 2. Square root of x squared is just going to give me an x. And then square root of 3, because the 3 can't break free. 75. 75 breaks up into 25 and 3. Again, 25 because it's on that perfect square list. So square root of 25 is 5. Square root of x squared is just going to be x. Then square root of 3. And this one doesn't have to reduce at all. That's just minus 1. Oh, actually, I'm sorry, I was wrong. It does need to reduce. Square root of x squared, that x can actually come out, but the number 3 has nothing that it can simplify with. Okay? I apologize for misspeaking there. Now, let's look at what we can do. All my radicals are the same, so it means I can actually add and subtract these together. So I have 2x plus 5x, which is 7x, minus 1x, so I have 6x. And then again, remember that square root of 3 doesn't change. Okay, square root of 3 just stays as is. All right, looking at the next one. So here we're dealing with cube roots. And again, the idea of a cube root is simplify when possible. So let's go back to our chart. Cube roots. So unfortunately, I don't see 250 on my list. But again, what I do see is a number that divides it, 125. So I'm going to first break this down into cube root of 125 and the cube root of 2. Same thing with the 54. So if I look, I don't see 54 on that list anywhere, but I see something that can divide 54. So I'm going to use that 27 to break it down. (27 times 2). Then 16. Once again, I'm not seeing 16 on my list, but what I am seeing is a number that can divide 16. All right, so I'm going to break this down into cube root of 8, cube root of 2. All right, so I break all of those down. So let's go back to the beginning. Cube root of 125 is 5. Then the 2 can't break free. Cube root of 27 is 3. But then again, the 2 can't break free. Cube root of 8 is, is 2. And then the 2 can't break free. So now, after I simplify, the neat thing is I see that I have some common terms, right? All of them have that square root of, or the cube root of 2. So I have 5 plus 3 of them gives me 8. 8 minus 2 gives me 6 of those cube roots of 2. All right, so that's the basis of being able to add or subtract these things. So now let's look at a word problem, all right? So in stained glass window design, the side of each small square is 5 inches. Find the perimeter of the window to the nearest tenth of an inch. All right, so each small square, so each of these little squares right here are 5 by 5, right? And then, of course, all of these are little right angles. Now, the problem is that 5 actually isn't anywhere along the outside of the stained glass, right? What's on the outside of the stained glass is actually that center going through it, those diagonals. Okay? So I can't just take 5 and start adding it up, all right? Because that's not going to get me anywhere. What I really need to be adding up are all of those diagonals. So we need to think about how can we find those diagonals, okay? So if you look at the drawing I have, do you see a right triangle in there? Because I sure do. Okay, and then what I'm looking for is that x, okay, that diagonal length. So do you remember the method for finding a missing side of a right triangle? So I'm hoping what you remember is Pythagorean's theorem. Okay, that is actually what it's going to take to simplify this. So Pythagorean's theorem says a squared plus b squared equals c squared. 25 plus 25 is 50. And then I need to square root that. So square root of 50 is that diagonal length. Now, the really neat thing though is that I can simplify this, right? I'm hoping right away, once you see that square root of 60, I'm hoping that you can picture breaking that up into square root of 25 and square root of 2. So that length is actually 5 square roots of 2 each, okay? So that's each diagonal. So if we want the perimeter, okay, we want the perimeter of this thing, we need to count up how many of those diagonal pieces do I have. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of those diagonal pieces. So I have 10 of those 5 square roots of 2, or 50 those square roots of 2. Now, actually, maybe I should backtrack a little bit. How do I know I'm counting up the outside? Well, because it's asking for the perimeter of that window, okay? So sorry, I kind of jumped ahead there. So the fact that they're telling me to find the perimeter is how I know I'm adding up all those outside pieces, all right? And it says to the nearest tenth of an inch. So what that means is because this is a word problem, it actually wants me to calculate 50 square roots of 2 is about 70.7 inches. Okay, so that is what this answer is going to end up looking like. All right, so that's adding and subtracting, all right? Now let's take a little bit of time to review another skill, again, that I know that you saw back in exponential algebra, okay? So, and in my class, you've actually already seen things like 2 plus I times 3 minus 5i, x plus 4 times x minus 7. So when you see things that look like this, ultimately you are talking about the same thing, okay? The strategy you used on both of those things above, you use here when you're multiplying two binomial radicals. And the strategy you end up using, obviously, is foiling, okay? So let's talk about, or let's review how to FOIL these things together, okay? And again, this is a strategy used when you're multiplying binomial radical expressions, all right? So to FOIL this, I get 1 times 2, which is 2, 1 square root of 5, 2 square roots of 5, and then square root of 25, which you guys, as intelligent algebra 2 students, all know that the square root of 25 is actually just going to be 5. So once I go through that FOILing process, now I'm just going to combine up my like terms. 2 plus 5 gives me 7. 1 square root of 5 plus 2 square roots of 5 gives me 3 square roots of 5. All right, so again, not too difficult, and I even know that you've seen this before. So Now let's talk about another one. So here, again, let's do the same thing, foiling process. 2 times 5 gives me 10. 2 times negative 4 square roots of 2. So the 2 and the negative 4 can multiply, while the 2 does not. 5 square roots of 3. And now in this last branch, square root of 3 times negative 4 square roots of 2, this time the 4 doesn't multiply, but the 3 and the 2 do. All right? And in this instance, if you look at every one of those radicals, I hope that you notice every one of those radicals has a different number in it. Okay, so what that actually means is I can't reduce this any further. Okay, this is actually as simplified as it gets. None of the pieces add or subtract. And let's do our last example. So square root of y times square root of y will be square root of y squared. But again, hopefully you guys recognize that right away as just y. Then here, the negative 7 stays out front, and the 2y combine. Here, the 2y combine again. And here, the 7 can't combine, but the 2 and the 2 give me the square root of 4. But of course, we know the square root of 4 is actually just 2. And we know that 7 times 2 is actually just going to give us a 14. All right, and finally, so the y and the 14 can't combine. But notice these, negative 7 square roots of 2 and positive 1 square roots of 2, that actually can combine. Negative 7 plus 1 is a negative 6 square roots of 2y. I could combine those together because I had the same thing inside those roots. All right. So again, a lot of good stuff today, some stuff that obviously you're going to have to remember. So in your summary, please reflect on the big ideas, the things that you want to make sure you remember, that you feel are important as we get closer and closer to our test on this. So once again, thank you for joining me. Fill out that summary and come back ready to do your practice work.